Okay, this is problem number 5. The figure shows a rectangle inscribed in an isosceles right triangle whose hypotenuse is 2 units long. And I want to just complete this picture. I thought better than having the whole picture up here was kind of draw it with you. So we've got a rectangle. I don't have the rectangle yet. I do have an isosceles right triangle. You can kind of see that. I'll erase this in a second. But here's your isosceles right triangle. So we have this angle right up here. That's our right angle. And the hypotenuse lies right on the x-axis. And since we said the hypotenuse is 2 units long, then I've got a 1 down here just to remind us it would extend out. If we have also our y-axis here, it extends out 1 unit to the right and 1 unit to the left. And again, we'll put a right angle in there. And I haven't drawn in the rectangle yet, so let's draw in our rectangle. But we have our isosceles right triangle. And now we're going to inscribe a rectangle. The base of the rectangle is going to lie right here on the x-axis. So we'll bring it up a little bit, and we'll draw our rectangle. And you'll note, unlike my picture that didn't come out very well, it should be symmetric. It should be kind of evenly balanced on both sides. And you might be looking at this picture arguing, no, I think you should have made that rectangle a lot wider. And I could have made it wider, but no, I didn't make it as tall. And I think, well, yeah, no, you should have made it taller. And I could have made it taller. But then look, it's not as wide. And that's our question in this problem is, how wide do you make it? Because the wider you make it, you're sacrificing height. Or how high do you make it? Because the higher you make it, you're sacrificing width. So how can you put that rectangle in there to actually maximize the area of the rectangle? So let's just sketch a model rectangle in here. And then we'll get out about our business here of actually maximizing the area of our rectangle. So let's just go with that rectangle. And let's call that point right there xy. If you wanted, because of the symmetry over here, we know that point would be negative x. And the y-coordinate would be the same. So negative xy. And so as you look at this, you can note immediately we have two variables. We have an x and a y. And so this problem kind of guides us through this, how we get rid of one of the variables. So here's part A. Express the y-coordinate of P in terms of x. And I should have labeled this point right here. This is point P that we're talking about. This point here, this xy, this point on a rectangle. And express the y-coordinate of P in terms of x. To do that, you'll note our right triangle here. We have this side right here, which is a line. It was an isosceles right triangle, so we know isosceles, both this side here and this side here are the same length, which gives us a 45-degree angle. So you know the slope is 1, or in this case, -1. And I can get the equation of that line or that side. It's y equals, look up here, the y-coordinate is 1, and the slope is -1. Or again, if you're not quite following that, you know that point here is 0, 1. This point down here is 1, 0. You can certainly find the slope. You can find the y-intercept. But this would be part A, and I wrote it in a kind of funny spot. But y equals 1 minus 1x, or 1 minus x. Our y-intercept is 1. Our slope is -1. So part A is complete. We have the y-coordinate of P in terms of x, 1 minus x. Now we come down to part B. Express the area, and I mean the area of the rectangle, in terms of x. So we come back here and we look at our rectangle right there, and we notice it goes x units to the right and x units to the left. We know the area of a rectangle. Area is base times height. So since we go x units to the right, x units to the left, the base is going to be 2x, and the height is going to be y. But if we read the question, they say express the area in terms of x. So now we look back up at part A. We've just done that. We have y equals 1 minus x. So I sub down here, my area is 2xy. I'll take out the y because y equals 1 minus x. So I get 2x times 1 minus x. I think I'll distribute 2x minus 2x squared. That takes care of part B. And again, this problem is kind of guiding us through. It wasn't maybe obvious how you would do that at first. So we've got the area in terms of x. The area is 2x minus 2x squared. Then finally, the optimization part, part C. What is the largest area the rectangle can have, and what are its dimensions? So we want to maximize the area. Fortunately, we have our area equation already, largest area. So now part C, I will take the derivative, a prime, I get 2 minus 4x. I'll set that equal to 0. I'm looking for critical points. My derivative is defined everywhere, so I'm not worried about my derivative being undefined. And when I solve that, I notice that x equals 1/2. Now, if I make a little chart with my first derivative test, there are no endpoints in this problem. But I'll look at x, and I'll look at a prime. And I've got here x is 1/2. Based on this problem, it wouldn't make sense for x to be less than 0, so I'll start from 0. Go to 1/2. Wouldn't make sense for x to equal 0 as well. And the biggest x could ever get is right here. It could not get any bigger than 1. So I'll go from 1/2 to 1. Now, when I sub in a value between 0 and 1/2, like a fourth, into my derivative, so I'll put a fourth right in there. 4 times a fourth is 1. 2 minus 1 is 1, which is positive, meaning my function a is increasing. When I go bigger down here in this interval from 1/2 to 1, like 3/4, so now I sub in 3/4 times 4 is 3. 2 minus 3 is negative, so a is decreasing. That is the only critical point on the interval, this x equals 1/2. My function goes from increasing to decreasing. My derivative changes from positive to negative at 1/2. And I want to make sure I give that derivative argument. I was kind of initially talking about the increasing, decreasing, but I really want to focus on the derivative. So at x equals 1/2, my derivative, a prime, switches. And it switches signs. It switches from positive to negative. Because it switches from positive to negative, I have maximized my area. So what is the largest area? Let's come back to our area function. Where did that go? Probably the easiest spot is right there. So what is the largest area? Area equals 2, x is 1/2, minus 2 times 1/2 squared. 2 times 1/2 is 1. 1/2 squared is a fourth, times 2 is 1/2, and 1 minus 1/2. The best I can do for my area is 1/2. And what are the dimensions of that rectangle? Well, keep in mind the rectangle, it was 2x times y. So x is 1/2. 2 times x. Let me just find a spot to put this. A little more paper here. So the dimensions of the rectangle, and again, keeping in mind going this way back and forth, it was x to the right and x to the left. So it's 2x. X is 1/2. So 2 times 1/2. The rectangle goes 1. And the y-coordinate, we come way back up to the beginning. The y-coordinate was 1 minus x. 1 minus 1/2. So the y-coordinate is 1/2. So come back down here and record our results. The x, it's 2x, so it's 1 by 1/2. So the maximum area is 1/2. The dimensions that give us that rectangle are 1 by 1/2. And again, it's going 1 this way and 1/2 up and down. And to be in this problem, we kind of talked about this tension. Do you make it wider or do you make it taller? You kind of see between 0 and 1, we split the difference, went right down the middle, and stuck with 1/2 for that. So that completes problem number 5.